that typically it's completed in about 2 days, and the strain rates usually used are between 3 and 5 10⁻⁶ second minus 1. I told you also that after 24 hours, the strain rate is typically 10⁻⁷ or slightly less, which means, or which explains, that the compression curves obtained in CRS tests and in conventional 24 hours tests are different, with the CRS test giving a compression curve at higher effective stresses than the 24-hour test due to strain rate. This has been observed on many clays, here Japanese and Quebec clays, and it can be shown that the strain rate is in this order, slightly less than 10⁻⁷, as I was saying before. And because of that, in fact, it appears that the pre-consolidation pressure obtained in CRS tests is typically 25% larger than that obtained in conventional 24-hour test, which means that if you want test for a CRS1, be aware that your calculated settlements will be much smaller than with the 24-hour odometer test. And this has been observed in Quebec, Japan, Finland, Italy, UK, Sweden, Hong Kong, Singapore. So it's quite general. Another aspect related to that is about what happens within a specimen. And Mesri and co-workers made special tests with specimens, with 4 specimens, 4 subspecimens in series, with the subspecimen 4 being close to the impervious boundary and the specimen 1 being close to the drainage boundary. And they loaded such specimens they loaded it to the same stress increase, and the results here are typical of what they observed. The specimen 1 is going to relatively high stresses, while specimen 4 goes to much smaller stresses. And the subspecimen 2 and 3 are somewhere in between. In fact, this can be explained as follows. Close to the drainage boundary, the strain rate is initially high, and so the soil goes to high strain rate curve, while far from the drainage boundary, as for here, in fact, the strain rate initially is relatively much smaller, and so the effective stress goes to lower effective stresses. And when the consolidation progresses, at that time the strain rates become more homogeneous within the specimen, and all the curves converge. So the fact is that the subspecimens in one specimen are not following the same stress-strain curve because of strain rate. So and we could add that the end of primary compression curve, which join this point and this one, in fact, is unknown from the soil itself. From these results, it's possible to define a set of isotac, constant rate of strain curves, and the subspecimen 1 goes to high strain rate, 10 minus 5 here, while the subspecimen 4 goes to the curve 10 minus 6 about. So this is consistent with the strain rate model. Another aspect which has been discussed a lot is to know what happens if we have layers, clay layers of different thicknesses. And this problem has been raised by Ladd et al. In 1977, and there are two extreme hypotheses. Hypothesis A considers that there is no viscosity during primary consolidation, and that whatever the thickness of the soil layer and whatever the strain rates, in fact, the curve, the stress-strain curve followed is the same during primary consolidation. On the other hand, there is hypothesis B, which considers that there is viscosity during primary consolidation as during secondary consolidation, and that consequently the compression curve followed in a thick specimen will be below the one obtained on a small specimen. So at that time, that would be the small specimen thickness, and here the thick specimen thickness. Another aspect, but which is the most practical problem, is that with hypothesis A, we will have a strain time curve like that, like this one, with the same settlement, say, at the end of primary consolidation, while with hypothesis B, the settlement time curve will be as the dashed line here, with a end of primary consolidation, which will be reached here. So the practical aspect is this delta epsilon, which is the difference in strain and then in settlement between that of a small thickness sample and a thick thickness sample. Donc, so that's a question which was raised in 30 years ago. This aspect has been examined by Mesri, who compared the end of primary consolidation of specimen having a thickness of 125 millimeters and specimens having a thickness of 500 millimeters. So they loaded these two specimens with different heights and obtained this compression curve. The green is for the 125 millimeters and the blue is for the 500 millimeters. They considered that the two curves were similar and that this was proving that hypothesis A is the correct one. However, we can raise few questions. Which difference are we talking about between the specimen with a thickness of 125 millimeters and that the one with 500 millimeters? In fact, hypothesis B, which is at the other extreme, gives a delta E of 0.06, which is not that much. But there is something more important, is how the end of primary consolidation is defined. In fact, Degago et al. In 2009 examined this data, in fact, and considered that we could define the end of primary consolidation at a given degree of consolidation. So, for example, 96% in figure A and 93% in figure in figure B. And so they looked at the results, but at the same degree of consolidation. And they came with the red curves for the 125 millimeters rather than the green here. The red curve here rather than the green here. And at that time, they found that the difference, there is a difference between the two specimens, and that this difference is not far from 0.06. And they concluded that hypothesis B is the correct one. Hypothesis B is consistent with the strain rate model previously described. So, clay behavior is controlled by an effective stress, strain rate relationship, and in fact this model can be extended but also can present limitations. Extension, in fact, the strain rate effect applies to all aspects of soil behavior and in particular to the underhand shear strength of the clay. And this has been shown by Kulawi and May, which are showing a normalized underhand shear strength versus strain rate, log of strain rate. And they come with, as a conclusion, that the underhand shear strength is varying typically by 10% per log cycle. Remember, 10% is also the change in pre-consolidation pressure per log cycle. So we get the same number. Another extension is that the viscous model, the strain rate model, can also include the effects of temperature. And this has been shown by several people, including here, but in particular by Eriksson, who performed CRS tests on the Swedish clay at different temperatures. And the results are shown here. You can see that the smaller the temperature, the larger is the vertical effective stress. And the pre-consolidation pressure, or vertical yield stress, is plotted here as a function of a strain rate. So there is a decrease with increasing temperature. And it has been shown that, in fact, the relationship obtained on Luleå clay is about the same as the one obtained on a variety of clays, as you can see here. So, in fact, the pre-consolidation pressure or vertical yield stress, which was a function of strain rate, is also a function of temperature. And this is shown here for the Berthierville clay, where you have the line in the middle at 20 degrees, the upper one at 5 degrees, and the lower one at 35 degrees. But when the vertical effective stress is normalized with respect to the pre-consolidation pressure associated with the temperature and the strain rate, at that time, all the data come in a very